So now we're going to start talking about exceptions to the octet rule. Yesterday we said that all elements want 8 electrons except for hydrogen. So if we were to look at an example like this where we have methane, CH4, we could say that carbon needs 8 and each of these hydrogens need 2. So that's going to be 16 that are needed. But what's really available would be your valence electrons. So you've got 4 for your carbon, 1 for each of those hydrogens, which gives you 8. So they're going to have to share. They need 16 to have a full outer shell, but they've only got 8 available. So if they share the rest of them, then they'll feel like they have a full octet. And so what we end up seeing is that it looks like that. And today is when I tell you that we kind of lied to you and did not tell you the whole story. And instead, we also have a couple other exceptions, and those would be beryllium and boron. So beryllium wants 4 and boron wants 6, and I know at home you can't see, but I'm pointing to the periodic table, thinking about where those things are on the periodic table, where we've got hydrogen, beryllium, and boron. So what they need is 2, 4, and 6. So if you think about where they're at on the periodic table, that might help you to really remember these. So these guys are not 8, they're going to be a little bit different. And I'm skipping over that. That was just to remind you about valence electrons. So then the other type of exception that we're going to have is that some of these can actually hold more than 8 electrons in their outer shell. And I know that some people kind of saw some of this when we talked about the maximum number of electrons in an outer energy level. When we have that D block, that's when it started interfering with some things. So these are called expanded shell groups, or expanded shell compounds, and they have more than 8 electrons around a central atom. And they do this by using the D orbitals there. And they're going to be those in the greater than the third period is where we're going to find those. And what you're going to notice about them is that you go through all of this, and when you try and come up with your answer, when you're doing your needed, available, and shared, you find an answer that makes no sense. So you just scrap the whole thing, and you start from the beginning where you just, you do that calculation for your available, but you'll connect all of those atoms to your central atom, and then make it equal your available. So I'll go through that when we see our examples. Okay, first couple examples have nothing to do with exceptions. And our first one, SO2. Is SO2 a polyatomic ion? No, it's not a polyatomic ion. It does not have a charge to it. So it is just a compound, SO2. We would draw our most symmetrical skeleton, just like that. Then we could figure out our needed, available, and shared. For our needed, how many are needed in this case? 24. How many are available? 18, because sulfur and oxygen both have 6 valence electrons. So 18 are available, meaning that there are 6 that are going to have to be shared. They need 24. They've only got 18 available, so if they share 6 of them, in other words, 3 bonds, then they can feel like they have a full octet. So 1, 2, what should I do about that third one? Just double it. Just throw it in there somewhere. So now, when we do this, and it doesn't matter where you throw that double bond at all. Right now, we're going to learn some rules here in a little bit. But right now, we're just saying it doesn't matter where that double bond goes. So when I look at this oxygen on the left-hand side, how many lone pairs do I need to add to make him happy? 2 lone pairs. Because he's feeling 2, 4, 6, 8. And again, it doesn't really matter where you put those lone pairs, as long as you keep those pairs together, you don't break them up, and then also make sure that you don't put it over here on the right side, because you have a bond there already. So if you keep it just separated on one of the other 3 sides. Okay, sulfur, what do we need to do? How many lone pairs? 1. And this other oxygen? 3. So last step would be to add them all up. 2, 4, 6, 8, 10, 12, 14, 16, 18. It's exactly what it should be. That's what's available. So always take the time to do that last step and make sure it adds up to the available. Okay, then we get to carbonate ion. This is a polyatomic ion because I see that guy right there. I'm going to start by putting carbon in the middle, my most symmetrical skeleton. I'm even going to do this right up front just so I don't forget about it later. because that's what we do with our polyatomic ions. You put them in brackets and show the charge. Okay, needed. 32, so all of these need 8. There's nothing strange about any of them. And then when we go through and do our available, we end up seeing what? Okay, so 6, 6, 6, there's our 18 plus the 4 is, wait, so 6, 6, and 6 is 18, 19, 20, 21, 22, and then we have to take into account the negative 2, so we add 2 more, so we get a total of 24. Oh, sorry, I put an 8 instead of an 18. So 18, wait, what did I do? I'm sorry, I don't know. Okay, this was 32. I think we said it right, but I just wrote it down wrong. So 32 minus our 24 equals 8. Did I do the math right? Yes. Okay, it's a hard math. So we need 4 bonds. 1, 2, 3, and again, doesn't really matter, just throw in another double bond. So carbon, any lone pairs that we need? Nope. He's happy. He feels those 8 electrons. What about this oxygen here? 3 lone pairs. Same with this guy. And what about this one down here with the double bond? 2. So just pay attention to when the bonds are a different number. You're going to have a different number that you have for lone pairs. So when we add them up, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, it's exactly as it should be. Okay, so these are just like we learned yesterday. Now we're going to get to our new stuff. Here we have, I don't know if I said this already, but boron the moron. Remember how that's a little bit different. So I'm going to take my boron in the middle with chlorines around the outside, and I can calculate my needed, available, and shared. Be careful on this. It's on that needed part that it's going to be a little bit different. So how many are needed? Right? 30. So it's 24 for your chlorines, 8, 8, and 8, plus 6 for the boron gives us 30. How many are actually available? 24, because that's 21 plus these 3 is 24. So we're going to have 6 that are shared. In other words, 3 bonds. Easy to figure that out. Make those chlorines happy. Give them a full octet. Same here. And how many do I add to boron? None, because he's happy already. He's got his 6 electrons. So that's it. And when we add them up, we get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So there we go. Everybody's good on that? And now we get to starting to get a little bit more challenging. You draw your skeleton structure on this, and you probably start thinking, wait a minute, this looks a little funky. There we have our 5 fluorines around the outside. Needed, available, and shared. How many would be needed in this case? We've got a total of 6 atoms, 48. So all 6 of those need 8 electrons. How many are available? Listen to the math going on. This is when we all wish we had calculators. 40. Okay, so we've got 35 for our fluorines plus 5 more for our phosphorus, which gives us 8, which means 4 bonds. And at this point you go, what? That's crazy. That makes no sense.
Oh, I get it.
That's what's important. That's what's important. So we see that it's crazy and it makes no sense. So if you look back at your rules, it means we're going to scrap this. And instead, we go back to our symmetrical skeleton, attach single bonds to every single element, and then give them full octets. Obviously, I don't have to do anything with phosphorus because he's already got more than he wants. We'll see if there's anything I need to do later. But for each of my fluorines, they're only feeling 2 electrons. 4, 6, 8. We'll do that for each of them. So then you go through and do that last step, and I'm just pointing to these so you can't really see this at home. But 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. It all adds up to 40. So we are done, and that's all we have to worry about with these. This is one of those examples where you have an expanded shell group. So notice that phosphorus is in that third period. Like we said, it has to be in the third period or greater for this to be able to expand, because we're getting into the D blocks. Okay, next one. Actually, this is just showing in 2 dimensions. That's what our Lewis dots show us. Again, this is 2 dimensions, but it's trying to show a 3-dimension picture of what's going on with those fluorines attached around it. Okay, a couple more. Here we have I3 with a -1 charge, so we have a polyatomic ion. I know on the homework people wanted to make some funny little circles or triangles, but you want to keep a central atom on these. I'm going to go ahead and put it in brackets with my charge. Needed, available, shared. Needed.
24.
Available. Right, so if you get 21, you should maybe look at that, and that would clue you in that you made a mistake, right? You can't just stop at 21 because you should not have an odd number. You have to add in this extra electron. So 22. And again, 24 minus 22, you get 2 divided by 2 gives you 1 bond. Silliness, that can't work. So we go back to what we know about expanded shells. We're going to say that we're going to come back here, create single bonds, then give everybody a full octet. So for this iodine, how many sticks? So 3 lone pairs. Same with this guy. And the central one gets how many lone pairs? 2. Now when we add up, I'm going to add these guys up, and I see 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's not right. We need to have it equal 22. So if you look back at your list of rules, it tells you if there aren't enough of those electrons, add additional electron pairs to your central atom. So we need 2 more electrons to give us that 22, and we added them to the central atom. Where you put them doesn't really matter. Just try and find a free spot there. Don't break up those electrons, and don't put them where you have a bond already. Okay, one more, and then you guys have time to practice. So XeF4. And needed, available, and shared. Needed. 40. And available. 28 plus 8, 36. So again, yes, you would get 4. You could try and go through that. That just doesn't compute. So we toss that. We go ahead, do our single bonds. Make our fluorines happy by giving them a full octet. I'm going to pause this and let people think about how many to add. Okay, everybody calculated. They came up with 32, that there's little dots that they've got right there. We need 36, so 2 more lone pairs have to be added. As far as those lone pairs, doesn't matter where you put it on that central atom, as long as you keep those 2 electrons together and try and avoid where a bond already is. So that is it. There's our expanded shell.